see if that overall force is acting within that middle one-third of the cross-section. Therefore, the gross cross-sectional area will be effective in resisting the combined axial and bending stress. If your eccentric load is within that middle one-third, that means that the force is still distributed through the entire cross-sectional area of the column, and therefore your entire cross-sectional area of the column will be effective in resisting the combined axial and bending stresses. So that is the first concept that's being tested in this problem, and that is very common to be done by NCES, because NCES likes to add a small little calculation or theoretical notion right at the beginning of the problem prompt or right at the end, or you can do both. And that is basically, if you miss that initial key concept at the beginning, that will just cascade down as you solve the problem. Or if you do all the calculations right through the problem, the small little theoretical notion or small little additional calculation at the bottom will basically throw all that to waste if you don't get that right. So understanding for this problem that the resulting compression force, because it acts within the middle one-third of the cross-section, understanding that that force still will be distributed through the entire cross-sectional area of this column member is a key concept that you need to use to move forward. So knowing that, we can then calculate the gross cross-sectional area of the column, which is simply the base times the height. And that is, it's a square column, and it's 32 inches by 32 inches. So that's 1024 square inches. The next step is to calculate the moment of inertia for that cross-sectional area. And that is going to be simply your base times your height elevated to the power of 3 over 12. This is the standard moment of inertia equation for square and rectangular sections. So a moment of inertia comes out to be 87,381 inches to the power of 4. Now P equals the axial compression force, E is the eccentricity, and C is the distance from the center of the column to the edge. Now, because the axial compression force is pushing downwards on the column, we're going to consider that as a negative force, just because we're using our notation on the vertical axis that any force pointing on the up direction or upwards is positive, and any force pointing in the down direction or downward is a negative. Now, the axial compression force is going to be simply the stress of the axial compression force is going to be simply it's going to be simple the division of the force over the cross-sectional area. And then because this is acting off-center of the column, we need to add this additional factor that increases the stress, which is the force times the eccentricity times the distance from the center of the column. So we can see that the eccentricity is 5 inches, and the distance from the center of the column to the column edge is 16 inches. And it's 16 inches because that's simply half of 32. So then we divide that by our moment of inertia, and we have that the stress on the column is negative 0.2 kips per square inch. Now the values given in the prompt are all positive values, but I consider them as being as all absolute values. And that's why we select 0.2 kips per square inch. See, the eccentricity is measured as 5 inches, as given in the problem prompt, and is shown on the diagram. Because her column is 32 by 32 inches, then the distance from the center of the column to the edge is just going to be half of that, which is 16 inches. So we've reached the end of our structural mechanics lesson. So let's go through a quick overview of the different concepts that we've reviewed during the past 6 hours. We reviewed dead and live loads. We reviewed trusses. We reviewed axial, shear, and bending concepts of forces and stresses. We also reviewed a small part of the combination of having combined stresses. Now this will be a small portion, if at all, tested on the breadth portion of the exam on combined stresses. Then we reviewed the properties of concrete materials, steel materials. Then we did a little bit on the material testing for those materials. Now note that the concrete properties, steel properties, and material testing, that also goes along the materials part of the PE exam. So you may have problems now that have the combination of different concepts in the exam. And last, we review concepts on slabs and on columns. Now, I want to point out some key appendices within CERM that you may want to have tabbed for the breadth portion of the exam. Note that some of the appendices in CERM also will apply for the depth portion of the exam if you're taking that part on the structural subdiscipline of civil engineering. Now, but for the breadth portion of the exam, I would like to point out Appendix 42.A, because Appendix 42.A will give you the sinusoids and area moments of inertia for very basic shapes. Here we see a rectangular or a square shape, where you get the moment of inertia, which is BH cubed over 3. And you have your moment of inertia at the centroid as BH cubed over 12. This is your moment of inertia bending about the x-axis, and this is your moment of inertia based on your centroid, which is, as you saw, what we just used to solve that short column problem. We also have it for other shapes like triangular shapes, trapezoidal shapes, circular shapes, quarter and semicircular shapes, and as well as a little bit more complex shapes. But the reason I'm pointing this out is because in the exam, you may have perhaps a trapezoidal shaped column or a circular shaped column where you need to use different types of inertia moments. And also you have the different areas and the different location of the centroids within those areas as well. So that will be applicable to the structural part of the breadth portion of the exam. Another appendix that I would like you to tab as a reference for the breadth portion of the exam is Appendix 44.A, which serves as a very good guideline on how to solve beam problems. And note that Appendix 44.A consists of 3 pages as it goes through many of the different cases of beam loading. And each one of these cases will provide you with the following information. First, what I like the most is information on the left side, which gives you the loading description, the shear diagram, the moment diagram, and the description of the deflection. And on the right side, it gives you the equations to calculate all of these. Most important, it gives you information how to calculate the maximum moment and how to calculate the deflection, which will be or could be some of the key items that you may be asked to find in the P exam. One other thing that you may want to use is the concept of superposition. So in the breadth portion of the exam, you may be tested with a loading beam that perhaps has one uniform loading that's just rectangular in shape, and that one uniform gradient loading that is triangular in shape on top of each other. So in the exam, you may have perhaps a problem that's loaded with something that looks like this. And the concept of superposition, what that will require you to do is to solve the equations for a uniformly loaded beam first, and then for the simple beam with the triangular load next. Another example could be if you have an exam that has a uniform loaded and then a point load right in the center. So then you will solve this problem for first the point load, or first the uniform load, and then for the point load. And if you're asked to find the maximum moment, you will simply superimpose the two to find it. And I'm sorry about that, I almost forgot. Appendix 44.8 is actually 4 pages long. So please be sure that you have all that identified when you tab it as a reference for the P exam. Now, Appendix 45.8 is also another important appendix that you may want to tab for the breadth portion of the exam. Now, these problems may yield a little bit more into the depth portion of the exam, but however, they still cover some common principles that you may want to know for the breadth portion of the exam. And this provides you the properties of different weld groups, of like if you're forming a shape of different welded plates. And you can see how the key thing that is clear to point out here is the location of the centroid and the section modulus, and of course, the polar moment of inertia. So if you're thrown something like this in the exam, you'll be able to calculate any of these values simply by referencing to Appendix 45.8. Appendix 47.8 is another important appendix to have tabbed in the exam, because this will give you information on how to find the fixed end moments for different types of beam configurations when you have fixed end connections. Note that all the connections shown here are fixed end, and note at the different types of load applications. So you may have a problem in the exam where you need to find the fixed end moment for any of these applications. Note that you can also use here the concept of superposition to find the fixed end moments. So for example, if you're being requested to find what is the fixed end moment at either A or B, right? Or let's say our part A for this type of loading, you will then solve for first, you can do either or, but let's say for this example, you first solve for the uniformly loaded portion, which is your negative WL square over 12. Negative W is the uniform load times the length, which gives you the force, and then over 12, which will give you the times the length twice over 12, which will give you the moment about A. So first you solve for the uniform load, and then you can solve for the point load. Simply, you will add the negative point load times the length over 8, and that will be your moment at support A. So Appendix 47.8 is another key appendix to have for the PE exam. So that takes us through the end of our structural mechanics lesson. Please note that this lesson is divided into 6 hours. So